did composite modeling and simulation. Some of you who know me, that I've been working in composite modeling and simulation for my entire life since PhD study at Georgia Tech. So I think some of you know that last October, the Nobel Prize in Physics was awarded to two scholars for their foundational research and innovations in artificial neural networks. And we do know artificial neural networks and AI is rapidly transforming many aspects of our technology and even our life right now. So awarding Nobel Prize to AI researchers is not surprising. What is surprising is the Nobel Prize in Physics, which seems suggests that the best physics-related research is artificial neural networks. Then we wonder that is physics-based modeling still needed? Should we continue to learn thermodynamics, continuum mechanics, elasticity, mechanics, finite element methods, and all that stuff? My personal belief is that the physics-based modeling is still needed. I will use a brief history of science to support my opinion. I don't know how many of you know this person I am showing on the figure. It's Tycho Brahe, and he did some careful observation of the planetary observations, and get a lot of data, did a lot of measurements. You know the second person? The second person actually is Kepler, is the person who actually worked as an assistant for Brahe and did a genius like curve fitting of that data to come up with these 3 laws of planetary motions. And we all learned it from high school or middle school, but we only know by name now. We don't know exactly what that 3 laws means. And the last person, of course, everybody recognize that that's Newton, who come up with Newton's law of motion and gravitation. And so this Newton's law is what I call physics-based modeling, and Kepler's law, I call it curve fitting. Then you have data. I really hoped, I wished, of course, it's not realistic, that that we still have access to Tycho Brahe's data. Can we use the most advanced AI algorithms to learn, to see whether it can learn even Kepler's laws? I don't think it can be able to learn the law of gravitation derived or discovered by Newton. So Newton's law, we do know that not only applies to the planetary observation, it also applies to the cars and the machinery parts and even the molecular dynamic simulation, they use Newton's law at that level. So this is the knowledge we need to focus on. And so particularly in the age of AI, as researchers, we should focus on creating Newton's law-like models. And also, this kind of models will not be replaced by AI. It's still needed, at least in my experience. From my opinion, I think needed for 2 purposes. It will be needed to provide high-quality data for AI to use. And second, whatever this knowledge, if it's codified in a tool like a simulation code, like like the molecular dynamic simulation code, right, can be used by AI intelligently to get the results with engineering precision. As I mentioned, that my area is composite structures materials, and I've been working in this area for more than 2 decades, close to be 3 decades now. In this field,
I think you've been muted. Can you unmute?
Wenbin, you just went mute.
Sorry, I clicked the wrong button. Can you hear me, Dr. Yu?
He's still mute.
Where I need to go for a mute?
Okay, can you hear me now?
Yes. Sorry about that.
Okay. So Guan Yu, as a host, you should be able to unmute me, right? Can you?
You are good now.
Okay, good. We'll continue. I don't know what happens there, but let's continue. Okay, so we build systems in the size of meters or hundreds meters, but because we want the high performance and lightweight, we use carbon fibers mostly and glass fibers. They are in the size of microns, and clearly that these composite structures, they are anisotropic, heterogeneous, and multi-scale. It's impossible that for us to capture the structure performance directly, still at the same time to capture the details of carbon fiber and all the reinforcements. So some type of multi-scale modeling and homogenization must happen. And of course, in the field, in the past several decades, we have numerous multi-scale methods developed, and but most of the methods are what I call a bottom-up approach. What I have been looking, because if you know my background, I started from how to model rotor blades. So it's a structure mechanism. I would like to look at the system from the top-down level. So for sophisticated system like Boeing 787, when you do structure analysis, it's a combination of 3D solids, 2D plates and shells, one-dimensional beams or thin-walled beams, depending on the geometry of the structure. Like if the three sides of the bodies of similar size, then you treat it as 3D body. If you have one of the dimensions much smaller than two other dimensions, you model it as a panel, could be curved or flat, which is share a place in the modeling concerned. Then if you have two dimensions much larger than the third dimension, you have beams. And the beams, of course, could be curved. And if you have all of the three dimensions, the order of magnitude different, you have thin-walled beams. Of course, when you model it, do the numerical analysis, you have beam elements and plate elements and shear elements. So from a top-down perspective, what we know is that to design structure, we first decide what kind of structure elements we will use. Then we identify how the structure made of, what kind of microstructure it has, what kind of information the material folks can provide us. So we could have what I called here the structure genes, the fundamental building block of structure. Then you effectively have two model representations. The method I created called Mechanics of Structure Genome, what it does is to minimize the information loss between the microstructure and the structural representation you needed at the system level. So it is a formal framework compared to most of other multi-scale methods that do not exclusively rely on direct information passing through the scales, but rather you operate from the homogeneous behavior you want at the structure level, then capture details at the scales relevant to a particular design needs. For example, we may want the torsional stiffness, bending stiffness of a wing in terms of particular wing configuration. Then it's also part of this framework can handle, and we implement our theory into a commercial, currently it's a commercial code now called SwiftCom, which can carry out a general purpose multi-scale constitutive modeling for composite structures and materials. And you will also realize that I define composites in a very loose term as long as it features anisotropy and heterogeneity. That's a composite material, not necessarily the traditional unidirectional fiber reinforced laminates. And the concept of structure gene and structure genome borrowed from biology. And structure gene is the smallest mathematical building block of a structure. So do pay attention to the word mathematical, which means if you can carry out the mathematical operation of representation to build the structure, then that will be okay. So you need to go to the smallest. Then structure genome basically composed of all the structure genes. You could have different structure genes for one structure, but they needed to form the structure. For example, that if you want to model the rod blade using beam elements, then each cross-section is a structure gene. But the complete set of the structure cross-sections used to represent the blade, that become your structure genome. And the structure gene could be one-dimensional. For example, if you deal with laminates, that's one-dimensional structure will be good enough. If you're dealing with unidirectional fiber reinforced composites, you can deal with a two-dimensional structure gene. And of course, if you deal with a beam, you deal with a cross-section. That's a 2D structure gene. But if you have, if your material, your building up block of your structure indeed feature three-dimensional heterogeneity, then you need a three-dimensional ST to represent that. And to further explain the concept of the mechanics of structure genome, I will use the beam theory, which is familiar to all in the audience right now, as an example to explain that how we do the problem, how it's related, how MSD related to the ancient theory of beam theory. For example, when we try to model a cantilever beam, what we do is that we need to look at the beam and what it's made of, then take its cross-section, and then to compute their so-called beam constants, EAG, EI, GJ, and GA, which is the transverse shear stiffness. And then we basically homogenize it to a one-dimensional problem to solve a deflection problem, for example. But we didn't stop here. We need to go back. So what we want is the longitudinal stress due to bending. So we have this formula here to basically kind of like do dehomogenization to get out what would be the critical stress. Then we do our design and safety margin and all that. And you will find out that this from the original three-dimensional structure to this one-dimensional representation is a homogenization. And this beam analysis is the microscopic analysis, what you want to call it. And then to get the stress in terms of the shear force and bending moment diagram, this kind of stuff, that is dehomogenization. And this procedure is the constitutive modeling. Of course, this does not appear in our undergraduate mechanics of strength of materials course. And because we make assumptions, then this calculation becomes simple. But usually those assumptions only works for isotropic homogeneous materials. When you go to composites, then a lot of assumptions are not realistic. And then you need a theory to do the constitutive modeling. But you still solve the same problem. What I'm saying, although your structure is made of more advanced materials enabled by the current manufacturing techniques. Okay, I also want to explain a little bit more about the structure gene concept. As I said, if this system level analysis requires 3D solids, then you look at your microstructure. If it's a layered material like a laminate, you want the 3D properties. Then you have a one-dimensional SD representation. If you have unidirectional fiber reinforced composite, you have a 2D representation. If you deal with woven composite, you need a 3D. And despite the different dimensionality of the you can call it the representative volume element, but it is not. I call it ST here. The 1D, 2D, 3D, what you want is, for example, for linear elastic analysis, you want the 6x6 stiffness matrix for your 3D elements. And also, after you've done the global analysis, you want to go back to find out what would be the critical stress inside the original microstructure. So this one-dimensional analysis can compute all your shear modulus, Young's modulus, Poisson's ratio, and also can compute all the stress components, although it's a one-dimensional analysis. Similarly for this two-dimensional analysis for unidirectional fiber reinforced composites, the same purpose can achieve. But most of other approaches, particularly finite element-based approaches, if you're based on 2D domain, you can only get the two-dimensional properties. You have to be tried very hard to get the transverse shear modulus, for example. Also get the out-of-plane space components. And the same idea can apply to panels. For example, you have a panel you want to model as a plate in your structure level analysis. If the panel is made of laminate, then you have one DST. If you have a corrugation along one direction, you have two DST. If it's made of woven or the stiffness run in both directions, you have three DST. What you want is the equivalent plate properties for your plate analysis. For example, that if you're dealing with Kirchhoff law plate analysis at this level, then you're talking about you compute the APD matrix from this guy, or from this guy. After you've done your plate analysis, you have force and moments, then you can do the dehomogenization to get the space happened at the original real structure level. Similar idea you can apply to beams. You have a slender structure, depends on the heterogeneity. If it can be a wound as if made of constant cross-section or piecewise constant cross-section, then you deal with a 2D SG. And if you have heterogeneity along the spanwise direction, for example, fixed wing aircraft, you do have heterogeneity along the spanwise direction. You deal with a 3D SG. And at the end of the day, what you want is the shear modulus, Poisson's ratio, shear center, all these beam-related properties for your beam analysis. After you've done your beam analysis, you can get 3D space. For those who are familiar with my research, this part was a significant part of my PhD thesis back in 2002. Yeah, I defended that 2002. That's 23 years now. And that is the basic concept of SG. Then if you want to go to theory, do some derivation, there are, of course, some equations, a lot of papers you can read. And but if you really look at it, there is only three basic steps. The first step is to express the kinematics of the original model in terms of the model you want, which is macroscopic model. For example, you could have, this is the three-dimensional displacements, but this U bar could be the displacement rotations of your beam theory. Then you have something you don't know. Traditional structure mechanisms called warping function. In micromechanics, we call it fluctuation function. After we have this displacement expression, we can get the strain expression in terms of the strains of the global model, and also some gradients of the unknown, and which is unknown. Traditional method usually assume to be certain polynomial of the smaller dimensions. Then we need to express the information of the original model. The information is whatever the behavior is governed. For example, if you're talking about the elasticity behavior, we know the principal minimum total potential energy can govern the elastic behavior. Then you write out the total potential energy of the original model. In terms of the model, you want to derive the global model. Then you minimize loss of information. Then this will enable you to solve for the unknown fluctuation function or warping function. And of course, this also basically unifies structure mechanics, micromechanics, because you could have this as a, displacement rotation of the beam theory or displacement rotation of the plate theory, and this still remain your Cauchy continuous theory. So, and let me use this as an example to show why this, beam theory is a structure theory, but it's also a spatial application of what we call the model scale modeling or micromechanics here, because you can view this reference line as a one degenerate continuum. Then every material point here, you have a corresponding microstructure to give you the effective properties. Now is the effective beam properties, and also to help you to do the dehomogenization or localization to get the local stresses. Okay, so that's simple enough. Then it depends on specific applications, and recently we derived a theory, basically this SG represented by shear elements. For example, you have a lot of current metal materials. They have very thin seals to make this heterogeneity. So the SG represented by shear elements, but at the end of the day, they want a geometrical beam theory. That can also be done. So this displacement will be in terms of, say, if you use resonant maintenance theory, it will be plate displacement and rotations. Then this will be your geometrical displacement rotations. Okay, we use a few examples to show how this method works, and This is the metamaterial and paper published in 2017 on Science. And what has been done there is they discovered a three-dimensional metamaterial with a trace. Basically, when you push it, it will trace. And in that paper, they used a high-order continuous theory to describe the behavior. But for me, I think it is a confusion between the material behavior and structure behavior, because if you have this unit cell repeated along all three dimensions, then you will find out this so-called traced behavior will disappears. And only if you have limited size, like form kind of like a plate or like a beam, you will have this extension or bending traced behavior happening. Of course, that is nothing new. We can use plus minus 45 degree laminate to generate that behavior. And if you view it from the structure level. So we did some work there, and we could reproduce what they observed there and publish a paper a few years back. And this MSG enabled us to do something very interesting. For example, the traditional model scale micromechanics, they homogenize to a point, but now we can homogenize to an element. So for example, in my global analysis, I want the truncated solid element, 3D solid element to do that. Then you have basically 60 degrees of freedom. So we can use MSG in such a way that whatever the original heterogeneous system matched here, you could have plate drops, all the heterogeneities and all that stuff. It can be homogenized to a solid element. That way, basically, you some way avoid the scale separation assumption. But the result would be a 60 by 60 effective element stiffness matrix, not the traditional Young's modulus Poisson's ratio anymore. And of course, you have this effective element stiffness matrix, then you can assemble it, then you can solve the problem. And after you solve the problem, you have the nodal displacements and all that stuff. You can do dehomogenization, get the space-strain distribution of the original heterogeneous material. Similarly, you can do a beam modeling. So for example, you want to use a three-noded beam element for your structure analysis, but your wings have significant tapering and you have heterogeneity along the span. And similarly, you can mesh whatever you hear, but when you do homogenization, depends on your structure elements you want. You will get, for example, if it's a single beam element, 6 degrees per node, you will have 18 by 18 effective beam element stiffness matrix. After you solve the beam problem, you can do homogenization, get stress there. And we have results showing that actually this type of approach performed pretty well and much better than Abacus solid composite solid element. And we have many other examples as far as the physics-based modeling concerned. And this is a chart to summarize what we have done related with the MSG and SwiftCom. Basically, it can take any arbitrary microstructure. By the way, that does not have to be a rectangular or cuboidal. It can be arbitrarily curved as long as you think as an engineer or an analyst, you think that's represented enough for my structure. We can take that block of material, do a homogenization through the principle of minimum information loss to get the equivalent structure properties, and also can perform dehomogenization to get whatever the stress and failure you wanted. And by the way, we also apply this very recently to the progress failure analysis. And it can use to perform the virtual testing of materials and structures, and also can be used to do the modeling of structures, not only just the composite laminates, but we can also deal with different structures, build-up structures, and sandwich structures. So that's good. Looks like we had a pretty good theory here, and the problem, but not completely solved. And so what are the challenges, particularly to use it for real industry environment, and what are the unsolved problems? And that's where the new game in the town, what the AI come into play. We started more than 10 years ago now. I think I had a student, they say, this material mechanics, composite mechanics stuff, pretty boring. I want to do something, popular, was machine learning and AI that time. So I challenged him, say, you need to think hard. What are the challenges that the traditional method cannot solve it? Then you can use it to solve. So we identified a few challenges. First challenge, of course, is high computational cost for complex 3D microstructures. For any of you did the model scale modeling, deal with complex 3D microstructures, you know what I'm talking about there. And also the second is that we idealize the microstructure. The microstructure through a complicated manufacturing process, usually not so idealized, and have a lot of randomness there. And also a lot of times that when you go to industries, they say, oh, yeah, I have the code that you can use to predict the composite properties. Then there's so many properties your code ask, I don't have. So there's unknown constituent properties and the constitutive models, which we make assumptions and as inputs for this type of methodology. Of course, that only one code is not enough, that one theory is not enough. This is only bridge the microstructure to the global structure, but usually we need to link to the manufacturing process simulation code and also integrate with the finite element, the global level simulation code or model body dynamic simulation code. So the interface with other codes to form the end-to-end simulation is not easy. That's the digital twin SME people are trying to solve. Then the last, of course, is not a big problem, but it's a big problem for small companies. You need to have highly specialized training to confidently perform composite simulation, and usually unaffordable for small companies. So those are the challenges related with composite modeling. And the first three can be solved by what I call the non-generative AI, traditional neural networks, and you can also interpret as surrogate modeling, sophisticated curve-fit surrogate modeling. The last two challenges can be helped solved by generative AI, particularly large language models. So AI-assisted composite modeling, and what we have done in the past almost 10 years, what we try to create the ultra-efficient surrogate model and also produce realistic microstructures, image recognition or generation. That's kind of like the possibility we identified, learn the unknown constituent properties and constitutive models. And very recently, we try to integrate different tools, use large language models, and also democratize the use of simulation workflows using a domain-specific large language model. And if you're familiar with what we have done, basically we're not using the machine learning as a black box like TensorFlow or PyTorch or other machine learning tools. We break it up. And also we try to focus on, say, what is unknown. For example, for a lot of our composite modeling, we make assumption of the material models. So we did in such a way, we break the material models in Abacus particularly, you're talking about UMass. So we basically use represent the UMass as the artificial neural network to be trained by whatever we measured at the global level. So we have indirectly make the global data. Then the Abacus, we still use Abacus in a sense. I mean, whatever other tools is similar idea here. And we still keep the kinematics, geometrical relations, and also the equilibrium equations, and replace the material models using a neural network to be trained. After training, of course, that become our numerical UMAT in a sense. And we did a training for the effective thermal conductivities, and that is basically you can take the continuous input and discrete inputs, and both geometry and material properties, and also woven patterns. This is a woven composites, and this kind of it's become pretty routine now. You basically solve the speed problem, and also can whatever the resulting models can be used for design. And we try to construct a numerical failure criterion for the yarn of a composite, because usually you have fiber matrix characteristic for failure, but you do not have for the young. So there's a possibility you can use model scale modeling to construct a numerical failure criterion for the young. Then you can calculate the failure of the woven composites. And we did, you can do a 2-scale homogenization from the woven to the yarn level to the fiber level. And also you can use machine learning, which is our deep learning model. We found out we can get a very close agreement for the predictions. But you do have to realize that the generated training data is a significant time cost. So it's only at a certain level you have to use the model many times, then you have a break-even point. So at least for this case, you will have at least 5 or 8 load cases to make it break even. And this one is basically what I mentioned, that they try to train the constitutive models using indirectly measurable data. And that basically, partially solves the lack of data problem, because usually when we measure the data, we use the ASTM standard or, certain limited test we can have. But if we can just, connect the data from the structures, for example, for here, I have a cantilever beam, I have a force here, I measure this point, get the full load deflection curve. And then, I can have this NN model embedded in my finite element analysis to train my NN model. And we found out that actually we have the possibility to learn a highly nonlinear stress strain curve for the material, and also if the material is damaged, we can also learn the damage and the strain relations as part of the constitutive relations. And this is a laminate. We learned the laminar constitutive model based on the laminate response. That's a similar idea. The previous is a homogeneous one. This is a laminate with a different layup sequence, but we don't know the failure criterion for the laminar and how it will fail. But I do have measurements at the laminate level. So that is what we come up with. We found out we can have a good agreement by using this methodology. So next that's basically what I call the non-generative traditional machine learning type of approach. You have paired data, then you do the training to try to use neural networks to come up with a surrogate model or infer some of our unknowns there. The generative, particularly the large language model, become popular in recent 2 years. And we did something, use generative AI to do inverse design. For example, that we developed a numerical regression transformer, basically using the masking and the tokenize the material parameters, so that you don't have to do an optimization problem to get the input if you know your output. So we did something like that. But in my mind, what's the low-hanging fruit for the generative AI, particularly large language model, is really help us to consolidate and deliver the knowledge we have, so that the sophisticated codes we have can put it into the everyday engineers on the shop floor. So let's imagine you have a platform can provide real-time, precise, authoritative answers, consolidating all knowledge in composites, integrate all tools in composites, and also incorporate all the insights of world leading experts. And also you don't have to talk in terms of highly technical language, but you just use natural language like the conversation we have right now. And it can be used on all platforms and through a chat interface like ChatGPT, and also engage the experts for quality control and reinforced learning. So that's what we have been working on in the last more than 1 year. We come up with a system called CompositesAI, the AI-powered composite expert system. And if you are into it, then you know what this truly what this architecture represents. But if you're not AI infrastructure oriented, it doesn't matter. I can tell you this particular specific features of this. This feature, I think by this time, I believe most of you use the ChatGPT, and this is talking about kind of like a ChatGPT for composites, but with the hope that we can deliver the authority like world leading experts and also precision like Abacus or SwiftCon or other codes you're familiar with. So for this system, you not only have the normal users like you use ChatGPT, we also have composites experts. They not only use it, but they also contribute and certify it. And they not only typical answers like a typical system involve, you basically have in the section here. We also hope to consolidate all the knowledge in our field. The knowledge actually could have three types of knowledge or data, what I call it here, static data in terms of papers, books, and reports and databases. That's what I call static data. Then you also have dynamic data, simulation codes. It could be physics-based or machine learning-based. And you could also have some data actually is not written in paper or codified in codes, but it's in the brain of experts. And how do we get those? That's called the tacit data. They are expert insights. We create a system in such a way we can basically leverage all this data and consolidate the static and dynamic and data, and also have the expert in the loop to kind of like distill the expert's brain. Of course, we also know in our field, the data could be public or proprietary, and you have your own secret source, and the system have the capability to make a private version of for your own company or your organization. You can leverage whatever is available in the public domain, whatever the experts would like to contribute, and also leverage your secret sources. And I will use a few examples to show what it can do. And this first is that you can ask questions and it will deliver your answers. And this is similar like ChatGPT, but if you ask a similar question like the upper bound of the Young's modulus for two-phase isotropic composite, and ChatGPT usually give you the rules of mixture according to Voigt definition, but they don't have this part, which it's only true that when the Poisson's ratio of that two phases are equal. If they are not equal, you have a different one. So this is the additional knowledge, what is called expert knowledge. It will basically provide the guardrails for it to be more precise. And another interesting capability that the large language model can help us to do is that we can use the human language become our input file and also become our programmable language. And you can through chat or through voice to execute sophisticated simulation codes and guide the process of prepare inputs and understand outputs. And this is actually motivated by a real story. And some of you know that in our center director is Dr. Byron Pipes. And he was trained before finite element was available. So usually if they want some questions related with micromechanics or something, they will come to me. One day say, Wenbin, I don't know how to find out the transverse shear modulus of a composite. Can you calculate for me? They say, sure. So, I open up my code and did the fundamental analysis, send him the code, send him the results, then come back and say, oh, these results are not realistic. Can you try different inputs? So I rerun it again. But that time we don't have the system available yet, the CompositesAI. Now we have the CompositesAI. I told him that you don't have to ask me these kind of questions anymore. And you can directly just use the system. Let me show it here. So if you look at here, I have said for unit direction fabric info, I would like to know G1, 2, and G2, 3. Do you have 2 or to help me to compute? They say, yes, I have 2, but it requires inputs. So I would say, I have isotropic fiber with Young's module Poisson's ratio, isotropic matrix, and hexagonal microstructure, and volume fraction. Then it will give me the results. And this prompt is directly from Dr. Pipes' email. They say, your numbers are a bit high, try EF and the Poisson's ratio of the fiber and the EM and Poisson's ratio of matrix. So that's what he sent me. I directly copied that email, put it here. And the system will take that prompt and recalculate, gave the results. And so that's one case showing that now we have the possibility to use the AI to execute such sophisticated micromechanics code or model scale simulation for us. The second one is that it allows the experts to contribute. I already mentioned this model. It was trained by Professor Xin Liu in UT Arlington. And usually as researchers, we did the model, we published paper, we are done. So what I did is I asked the model he trained sent to me. I dumped it to CompositesAI, and it now make it live and can be used to answer a lot of questions. Let me show it what I did here. Say, I just take that model. I didn't do, of course, you have to make it to be API compatible, and the large language model can understand. And say, I want to, now we have the model in the system now. I want to find the effects of fiber volume fraction or thermal conductivity of woven composite. Can you help me? So the system basically intelligent enough know that you want to do a parametric study based on a tool available in the system. It automatically varies the volume fraction and compute the corresponding thermal conductivities for me. So I want to make sure they are not just to make up the stories for me. I say to compute thermal conductivity for a plane wave composite, what inputs do you need? And it will list all the inputs. Then I found out, wow, you don't have inputs for where you don't have thermal conductivities for fiber matrix. Then actually the system is intelligent enough, say, because when I do the training, the model assumptions, those variables are fixed. So they are not as one of the design parameters or the model parameters for me to train the model. Okay, I say, okay, now I understand. So can you run optimization for me to seek the minimum of the in-plane thermal conductivity and maximal out-of-plane thermal conductivity among all the inputs you can explore. So they actually can vary design input or whatever model parameters as a design space and run out the optimization for me for different configurations. I will also say, that's the same one. I also ask that, can you treat the different volume patterns as design parameters to run this optimization again? Then the system can do it for different plane wave trail and 500 staging. They give me the results, what they find out, the corresponding maximum, minimal thermal conductivities. So we basically, with the large language system, with the AI, we can make whatever originally kind of like static on a paper now live, and also the use of the model become, significantly expanded. You don't have to write the optimizer yourself. The AI knows how to do optimization. You don't have to do the parametric study. AI knows that how to carry it automatically. You save a lot of effort for doing that. And as I mentioned, that we also need experts in the loop, because AI could make mistakes and often make mistakes, particularly depends on the data you put in. And so we build a system that basically experts and AI can interact. Not only experts can contribute data and certified knowledge in the system, but also can interact with AI and with other not experts. I have an example here, if you look at here. So this is a question asked on this platform. It's from Europe, I think, this student. And they asked, send me email to ask question first. I say, why you don't ask on the platform? So I replied to the student. Then I realized, the student also thanked me, for my answer. Then the admin say, why we don't try the AI? So we can add CompositesAI, say, can you answer this question or not? Then AI basically began to answer questions for me on this platform. And if you compare the answers, you will find out that if it's not better, at least as good as what I answered that student. By the way, this question is directly related with my course, so I'm claim myself to be expert there. Then there are another student kind of like, kind of skeptical of AI. He threw the questions into ChatGPT 03 and get the answers. Then I look at it. Indeed, it looks like, if you look at the ChatGPT's answer, looks like very expert, even more extensive. But when you meet the real experts, they use the 03, Chat 03, and you will find out that I identified how many errors in ChatGPT's answers. You do need the expert in the loop. You do need to rely on expert knowledge to deliver trustworthy answers if we use AI. And I think this may be my last slide. No, let me see. Okay, yeah, that is what I have. Yeah, I have 2 more slides. So you can try the Composite AI system is live for able to use, and also you can try the AI human interactive platform. And as a summary, that the way in the past we developed the Mechanics of Structure Genome really basically unifies the physics-based composite modeling in terms of micromechanics and structure mechanics. It can deal with all structures made of anisotropic and heterogeneous materials, and we don't have to invoke the invalid scale separation assumption. Sometimes scale separation assumption is valid, sometimes it's not valid, particularly your representative volume element is not small enough comparing to your structure you deal with. And MSD can achieve the best accuracy at giving efficiency of certain engineering model in terms like Baloni model or Tim-Cinco model or resonant mean model or Kirchhoff-Lam model. By the way, we still use these names, but we don't use corresponding assumptions. And the AI can help us to reduce the computational cost and create the more realistic microstructure, discovering the unknown physics information, and also consolidating and delivering the expert composite knowledge. The expert composite knowledge, as I mentioned, not only just the static knowledge like papers, textbooks, and all that stuff, but also the codes and also the tacit knowledge, which is the experts' insights in their brain. So I will stop here and take any of the questions you could have. And by the way, if you want to try the system, you can scan the code.
Fantastic. Well, thank you very much, Dr. Yu, for your excellent talk and for joining us today. We really appreciate your time and the knowledge you have shared with us. I wonder if people have questions to ask. You can unmute yourself and ask any particular question. I am glad that we will be able to use these tools whenever we can right now. So this is for free? Is that right?
Yeah, this is for free. Yeah, at least unless this usage is so significant that the cost become unbearable. But at this moment, I think it's okay. And it will be free for foreseeable future.
This is great. Yeah, I tried to use ChatGPT asking composite questions, but it's very limited. There is not much out there, and I'm very pleased and thankful that you are taking the initiative to have very compressive AI technology for composites. So I have some questions actually. You may already cover them, but I want to make sure I understood. So for example, one of the questions is, how do you ensure the accuracy and physical relevance of AI predicted behavior, especially under failure conditions and nonlinear loading?
Yeah, that's basically why you need an expert in the loop. If you look at the system, the system allow you to do the feedbacks. Let me look at here. Let me forward ones. So by the way, you can also do plus in the chat system. It will allow you to do the feedbacks, and you can provide the feedbacks that it really doesn't make sense. For example, you will say, this one is maybe I may sign up on that. Let me see this one. Yeah, so you can read it and also you can read it and you can also tell the reason why, and you also can provide feedback to us. And also you can also go to the community.cdmpa.org to debate or discuss with others. And we will collect this information and also further refine it. And if you remember, if you keep watching the generative AI and the large language model, when ChatGPT was first released, 2023, I think the end of the year, and it was laughable, the results. But now it's getting more and more accurate, and for most of general tasks, it's pretty good. So yeah, at this moment, maybe it's mostly my knowledge. I think questions related with my knowledge, they're pretty good. But for some other knowledges, we need more contribution and we need more feedback to help improve the system.
Sounds great. Well, thank you. Anyone have one question? Questions for Dr. Yu? Otherwise, I have one more question. Meanwhile, people think about it. The other question is, you maybe already also mentioned this. How do you handle data scarcity for rare or difficult to measure material behaviors?
Yeah, that is also kind of like one of our concern, that the data, not enough data. I think mainly it's not enough data, but it's how do we basically curate the data to basically make use of the data. And recently I have one of my not PhD, but the master degree student try to basically how to, thinking about how many people run ABAC simulation right now, in the whole world. Maybe there are thousands. So how do we automatically curate that data and use that data to update the AI system? That's basically, if we can find a way to do that, then we don't have to worry about the data, particularly also for the measurements. Also, that's also a valid concern. But we just need to change how do we connect and curate our data, and also how to measure the data. As I mentioned, that you're not necessarily just use ASTM standard to measure data. All your data in the operation, if you look at that example I showed, let me go to that example. Let me say the cantilever beam example. It's teams I'm not very familiar with, so it takes me a while. So if you can measure data this way, then you really don't have to worry about lack of data. Now you can put sensors almost everywhere, and you can connect the data, and that's also part of the digital twin people trying to do.
Sounds great. How come we can work to collaborate with your community or with your university and your group of researchers?
Collaborate, you mean?
Yes. Well, how do you usually partner or work with somebody else, another researcher? Or
yeah, I think it's, if you're person into sharing, you can basically become an expert on CompositesAI, and then you have you can contribute your knowledge and your tools and to be used by the entire community. And of course, for that CDMP community, that AI interactive community, for this community, is just a technical forum. You can post questions, you can have answer questions, you can also interact with the AI as a chat there, and that everybody know. And this is kind of like a ChatGPT for composites, but it has the possibility you become one of the developers to contribute your own domain knowledge there. And also, when you contribute domain knowledge, you don't have to share with the general public. You can choose whom you want to share to. You say, for example, JPL. This group, you want to only share whatever the composite group at JPL. That's also possible. And the system allows you to do it.
Sounds great. So we kind of almost there in time. We still have 1 minute and a half. I may have one more question, but it's is not quite directly with what you were presenting today. Anyone else have a question before I do the last one? So my question is related with the last talk that somebody gave in Sampe by Dr. Sinkan Pila. It was also related with AI. The title was AI in Composite Materials and Manufacturing. Can you let us know what is the difference, or if there is something similarities, or what he presented with yours?
Yeah, that's a very good question. I actually watched his talk, Dr. Pilar's talk. I think that was maybe 1 or 2 weeks ago. And what he's doing is try to use generative AI to basically how to model the system better, for generative or non-generative. Particular thinking about he has a diffusion model, which is part of generative AI, to try to basically do inverse design, what I mentioned. Say if you have a nonlinear space spin curve, what kind of microstructure you should provide. So what he is doing could be part of the system that can become a tool or a model, so that it can be deliver answers to the designers, to the normal engineers in industry. And we, as I also mentioned, we tried this kind of approach ourselves before. We haven't seen the significant advantage yet, but of course it's still a very good research project. And you can basically, without doing the inverse, the optimization, the inverse problem and local optimum or minimum, whatever the traditional method could reach. If you use the inverse design, we developed the numerical regression transformer. It can automatically find whatever the microstructure or corresponding the fiber property or matrix property needed to achieve the effective composite property. We have that done. We recently have a graduate student just graduated. But unfortunately, that he will become an AI ML engineer for Dassault systems. So he will not continue working in this direction. They were doing using AI to do something for finite element codes.
Fantastic. Well, thank you very much, Dr. Yu. Thank you for your time. So I think this is conclude our presentation for today. And I will share the recording with everybody else. Thank you very much.
Thank you all. That I think Juan has my contact information. For those who don't have my contact, you can email me or just go to LinkedIn and we can connect that way. If you have further questions or you have some insights to share or criticisms, just shoot me email. Thank you.
Thank you very much. Have a good day, everybody.
Bye-bye.
Bye.